In order to analyze a pumping test, we need to first obtain field data. Typically, this means measuring the drawdown and the flow rate as functions of time. Then we need to identify a mathematical analysis that's able to simulate the field test. Typically, what this means is that the analysis needs to match the assumed conditions for the test. There are a variety of conditions that we'll assume. One would be what's happening at the well, and so we could have a constant pumping rate, a constant head at the well, perhaps other things. We need to assume what's happening there, and then we also have aquifer boundaries. Is the aquifer of infinite extent? Is the aquifer truncated? Is there a stream out there and the aquifer and the stream is cutting down into the aquifer? All of these effects will cause the pumping test to be different, and it'll affect how the mathematical analysis is done. A leaky confining unit is also something we could consider, and it will change the mathematical analysis that we use. So based on the geologic setting and how the pump is set up, how the well is designed, we'll come up with a mathematical analysis, and it'll be able to predict what the hydraulic head is as a function of time for a given flow rate, if that's the kind of test that we've just run. And so then the strategy is to adjust the parameters in the analysis. The way these analyses work is that they'll predict the hydraulic head, but they require you to tell them what the transmissivity and the storativity and perhaps other parameters are. So you try out a set of parameters and see how well they predict the data. So it would go something like this. If this was the drawdown as a function of time, you have data that look like this. And you pick an analysis and try some parameters, a value of T and S. You get a curve like that. And then you adjust it and perhaps get a curve like that. It's one's a little bit too high, one's a little bit too low, and then you select another set of parameters and get a curve that looks like that. And that you say, well, that's the best fit that I can get between the predicted heads and the observed. So this curve here will be generated by a value of T and S and perhaps some other parameters. And so you say that those values of parameters are the best fit, and those are going to be our best estimate for the parameters of the aquifer. So the procedure of adjusting these parameters and evaluating the fit can be done graphically. You can plot data and you can plot the function that you're trying to fit and do it graphically by hand, or there's also a variety of numerical procedures that can be used to do this analysis using a computer. So a classic analysis of this problem was done initially by Theis, and this analysis has the following assumptions. The pumping rate at the well is constant. It's a confined aquifer, and it's of infinite extent. So there are no boundaries. The aquifer goes on forever. It's homogeneous and isotropic. The analysis is transient, so it's a function of time, and there's no recharge. So with those assumptions, the analysis can be set up like this. This is the governing equation, and this is hydraulic head here. That del squared, that's the Laplacian operator. It's the second derivative in x, y, and z. And here on this side we have the hydraulic head as a function of time. There are our parameters: storativity, hydraulic conductivity, and aquifer thickness. And we know those combine to give us transmissivity. Okay, so that's the governing equation. The boundary condition at the well is that the flux at the well is equal to the pumping rate, which is constant, divided by this stuff, 2 pi, the radius of the well, and the thickness of the aquifer. And the other boundary condition is at r equals infinity, and it says that the head is equal to the initial head. Okay, so that's the mathematical problem. And as it turns out, that this problem can be solved fairly readily. And Theis recognized this many years ago and published a paper that says that the drawdown as a function of time is equal to this thing here. And so there's the pumping rate and the transmissivity there. And then we have this integral. If we pull that out, this guy here, that is what's called the exponential integral. And the math guys use this E1 as a function of u to describe the exponential integral. And you can look this function up in tables. You can see how it's plotted. It's fairly straightforward. This term u, if we look at it down here, it has the radial distance, the storativity, k and b, all parameters, and then this term here, time. So we can think of u as a function of time and as a function of the radial distance. So this is how we could plot the drawdown as a function of time or as a function of radial distance. Those two terms enter right there into u. Okay, so we can write this in a compact way like that. So drawdown is a function of these constants and this exponential integral that's a function of u, and that's where we have the time and the radial distance. So that's how the math guys would describe how to solve that problem. What was done, what Theis and the people that came after him did, was to say, well, this exponential integral, maybe that's a little bit scary, and so we'll call that, instead of E1, we'll call it W, and that is a well function. Okay, so this term W is describing how the well is behaving as a function of time and as a function of space. And there's the U, same U that we had before. And one way that we can think of U is if we take 1 over U, we get this. And here we have time, and this block of terms here, that has units of 1 over time. So this whole term here, 1 over u, can be thought of as a dimensionless time, as time, the actual time right here, scaled to these parameters of the problem. And so this is called a dimensionless time, and these well problems are often written as a function of dimensionless time. It allows you to plot the results, for example, as a function of this dimensionless time, where the function is changing just like it would change as a function of real time, but all of the parameters are embedded in it, so you don't have to assume what the values of the parameters are in order to plot the results up. Okay, so if we take all that in perspective, we have this W as a function of u, and we can think of that as W as a function of 1 over the dimensionless time, and that's the well function. So we write it like this, where drawdown is a function of the constant times this well function. So that's what Theis did. Let's go back here a second. That's what Theis did. And this is something that you can readily use to fit data. So this function here, this WU, it looks kind of like that. And if you plot up drawdown as a function of time, if you plot up data from well tests, it kind of looks like that too. And so you can adjust the parameters and get it to fit. The problem with this is, though, that in order to evaluate this function, you really, well, it's possible to do it graphically, but it's much easier to do it with a computer. So if you're using a computer, you can readily do this fit and get a fit like I'm showing here. But it's a little bit tedious by hand, and so actually that ended up being a fairly serious problem, because back in the day when Theis first suggested this, the computers hadn't been invented yet, and so they were doing this with slide rules, and calculations really of any type were quite tedious. And so what happened was this guy Jacob recognized a few years later that this exponential integral could be approximated in a way that was a lot easier to evaluate, and really it lended itself in a much better way to graphical evaluation and to evaluation just by simply plotting it up and fitting data by hand. And that was much easier back in the day, and it still is easier and can give quite good results. And so this is an analysis that I think would be worthwhile learning, and it's what we'll use to analyze the pumping test that we do, at least at first. So here's the way Jacob analysis goes. So there's U to refresh your memory. And as it turns out, if you go and look up this exponential integral in a math handbook, what you'll find, and what Jacob found, was that it expands out like this. So this function has what's called a series expansion that looks like this. So there's U, and then you have these factorial expressions. And this thing here is called the Euler number. So it's just a constant. And so what you get from that is that as, well, let's take a look back up at U. As time gets bigger, then U gets smaller. So as our test goes on and goes longer and longer, U will get smaller and smaller. And so the way this series is going to work is that if you take a small number and cube it, you get a number that's smaller than that number when you square it. So this number here, as U gets smaller and smaller, that number will become much smaller than that number. And at some point, we'll say, well, we can just ignore that. And then as time goes on further, U squared, it gets to be much smaller than U, and we can ignore that one. And then as time goes on further, U gets much smaller than the log of U, that's the natural log, and we can ignore that. So if we ignore the early time, so when we first turn on the pump and we start pumping this well, and the drawdown is happening, if we ignore that stuff and instead focus on the data that comes later, and just exactly how much later we just have to figure out. But what'll happen is that the longer we go, the more that this problem will end up, the more that basically this term here will start behaving like that. Okay? And as it turns out, for many practical situations, you don't have to wait very long before this is a good approximation of the overall well function. Okay, so that's going to be pretty helpful because this is just the natural log, and that's a lot easier to evaluate than this exponential integral. So what we'll do is say, okay, we're going to forget about that early time, and we're going to analyze the late time in the pumping test, and then the exponential integral can be approximated like that. So it's approximately equal, but we think that it'll be close enough so that we'll be able to get a good analysis. All right, so now what we do is say, well, if this is true, then I'm going to write that as log of 1.78 because this is just a constant here, this gamma, and that's given up here, 0.577. So the natural log of 1.78 equals 0.577 and so on. So this term there goes to that term. And then I can combine these logs. So that is written like that. And then I can go back up here and get U. and substitute it in, and that's what I get. Okay, so we have this exponential integral well function, and the real clever thing that Jacob did was to recognize that that could be approximated by the natural log of this stuff. And this is all stuff that we know. There's the transmissivity, well, that we either know or that we want to find out. So there's transmissivity, there's time, there's the radial distance where we're making the measurements, and there's sortivity. Okay, so that's the basis of the Jacob analysis, and we go and plug it back into the function of that gives us the drawdown, and so there's drawdown as a function of that stuff we just saw there, and then we have this constant out in front, the pumping rate and the transmissivity. Okay, so here's what we do. The natural log, that's pretty easy to evaluate, but the base 10 log is more common, and we want to use log graph paper. And so most of the graph paper that you have, if you go and plot log axis in Excel, for example, then it uses base 10 log. So we want to switch this from a natural log to base 10, and the natural log is equal to 2.3 and change times the base 10 log. So this guy can be changed to that guy, where we just change from a natural log to a base 10 log, and the only difference is that we pick up this factor of 2.3. Okay, so that's pretty straightforward. And then what we're going to do is write out this. That's going to be that just the log term. When we have this argument here on the inside of the log term, we can write that like this. We can write that as log of time plus log of all the other stuff in there besides time. So 4t over 1.78 r squared s. Okay, so we've just expanded out this term, and that's what we get here. That's what the next equation is. This 2.3q over 4 pi t, that comes along for the ride in both terms. All right, so now the next step, and once we do this next step, we'll pretty much be there. If we take the data and plot it up on a semi-log graph paper, so we're plotting the time axis, the x-axis, on a log scale. So if we do that, then this function here has the equation of a line. And here, this is the equation of a line. This guy here, the intercept, that's b. This guy here, that's the slope. We'll call that m. And log of time is just now x. Okay, so if we plot the data up on a semi-log axis, then we get this straight line. Well, remember back a couple videos ago when we plotted up data, it looked like this. If this was log of time, and this is drawdown, we saw that the data kind of looked like this. Remember the color screen where we saw the colors changing around the pumping well, and then there was also a graph that was proceeding, and it went up and kind of leveled out like that. This part here was a straight line when we plotted it as a semi-log, and that's the same straight line that we're saying here from the Jacob analysis. Okay, so here's the real beauty. If we fit this part of the data with a straight line, then we determine the slope, and m is the slope. So the slope of that line from our data is equal to this. And that equals, if I just then combine these numbers, that equals that. So if we measure the slope, and we already know q because we've held that constant, So if we know slope and we know q, we can simply solve for t. So measuring the slope of this line here ends up being the way that we'll calculate the transmissivity of the aquifer. Okay, so we've got transmissivity, or at least we've got a way of getting that. Now what we need to do is come up with a way to estimate the storativity. So let me go and draw how the data is going to look. So we have data that looks like this. This is what is going to happen. So this is now log of time. Let's call it log of time. And we get this semi-log straight line. And when the data start to become a semi-log straight line, then the Jacob analysis applies. So we come out here and find the data as a semi-log straight line, and we fit a straight line to it. We take the slope, and that allows us to get t. And then what we do is extrapolate this back to here, to the point where the drawdown is equal to 0. Okay? And that'll give us a particular time. We'll call that t sub 0. So the actual data aren't doing this, but we're approximating the data with this Jacob analysis, and it's saying that at this time the drawdown will equal to 0. So we come back here and say, okay, well, what has to happen to this analysis so that the drawdown is equal to 0 when the time is equal to this t sub 0? Well, the answer is that this guy here, the log of 1 is equal to 0. So if we put a little t0 there, when this term here is equal to 1, then the log is equal to 0 and the drawdown is equal to 0. Okay, so what we have to do is then find out what happens here. So that is the condition for the drawdown being equal to 0. And we know everything here. We know that. We know t sub 0 because we measured it off the graph. We already know transmissivity because we just calculated that from the slope. R squared is the radial distance of the monitoring well where we're making the measurement. And so we know everything but S. So we solve this one for S, and we get that. And then what I did just to make things a little bit easier is I combined these numbers. 4 divided by 178 is that number. So that gives us now two equations for T and S, and that's shown here in the green box. So the strategy is take the data, plot it up, fit a straight line to the late time data that's creating a semi-log straight line. The slope of that we use in the first equation to get transmissivity, and then the t sub 0, the intercept, the place where the time where the line that we've drawn intersects the drawdown of 0, that's used to calculate the storativity. Okay, so once we have done that, we've calculated T and S, then we can go back and use the Jacob analysis to predict the drawdown. And there'll be two ways that we'll do this. If we fix this guy, fix the radial distance, and then let time vary, that allows us to calculate the drawdown as a function of time at a point. And this is typically going to be called a type curve. So drawdown as a function of time is a type curve. And then if we fix t and let r vary, then what we're doing is we're getting the profile of the drawdown at a particular time. And that's shown here in this second graph. And so this is at some time, I'm not sure what it is, but at a particular time we have the drawdown as a function of the radial distance. So this would be the profile of our cone of depression right here. And both of those curves are developed from the Jacob analysis, and we can plot them up once we've determined T and S. Okay, so this ends up being quite a handy prediction tool, because once we've determined T and S, we can now predict what the drawdown is at a particular time. What the drawdown is as a function of time at a particular point, and what the drawdown is as a function of space at a particular time. Okay, so now we want to take the next step and analyze what happens after we shut the pump off. And that will allow, when we shut the pump off, then the water levels will start to rise and the system will approach the equilibrium. It'll go back to the original conditions. And so we're measuring water levels then, and it would be nice to be able to use those data as well. So as it turns out, we can do a simple little trick to take the Jacob analysis that we've developed for pumping and use that analysis to analyze the recovery of the well. And so here's the way it works. This is a pumping test here, this plot, that shows the flow rate as a function of time. And you can see it's got this this rectangular step to it. So the pumping period is shown here, and we pump for a while at a constant rate, and then at time t1 we shut the pump off, and then that's followed by the recovery period. Okay, so we can think of this step-like behavior as really the addition of two types of systems. One is shown here, and I call it regular Jacob. This is pumping at a constant rate as a function of time. We start off at time equals 0 and we just keep pumping. And so this is the formula that we saw earlier, and it says that the drawdown just keeps going. But at some point we shut the pump off. And so what we do then is we generate another analysis, and this is going to be done with the Jacob analysis, but instead of starting at time equals 0, we started at time of t1. And instead of having a positive pumping rate, we have a negative pumping rate that's equal in magnitude to the positive pumping rate. Okay, I'll show you how to describe this with the Jacob analysis in just a second, but the interesting thing here is how this works conceptually, because if we take this and we add to it this, then in the beginning this second expression here doesn't do anything, but once we reach t1, the negative flow rate offsets the positive flow rate and causes the flow rate, the net flow rate, to go to 0. So if we take this and add to it this, we end up getting the original step-like thing that we're talking about. So this is a process called superposition, and it allows us to take the original analysis, the Jacob analysis, and by adding together two versions of it, we can have it, we can kind of extend the conditions that it's applicable over. So here's the way it's going to work. Let me just erase this writing here. Okay, so here's the way it's going to work. This is the drawdown during recovery, and this first term is just the regular Jacob expression. That's what we saw on the previous page. That's this one here. This one is shown here, and here's the way it's working. It's a negative flow rate, so we have a negative sign there, and the time starts at t1. So if we look here at the original Jacob, that time there starts at 0, and then here here we have t minus t1. So in this case, when the time equals t1, this whole thing equals 0. When time equals, say, 1 plus t1, so when the time equals right there, and there's 1 unit. When the time equals 1 plus t1, then by doing this, we subtract off t1, and this thing just gives us 1 unit of time. So this is going to behave at t equals t1 plus 1, just like this one does at t equals t1. So if that's 1 unit. So the way that this is working is that where we're using here t minus t1, it's just basically sliding the analysis back so that even though we're starting right here at this time, it's as if this point right here was a time of 0. That's what this subtraction does. Okay, that's the only change though, is that minus sign and then this minus t1. And that allows us to generate this expression here, or something that represents those conditions. And so then when we add these two together, we get this. And the way that this is going to work is that we have the first part here, that's going to be valid during pumping. And then this second part, both of these two terms added together, will be valid during recovery. Okay, so there's that, and there's that part. And here's what we do. Let me go, and we'll do two things here. We're going to take this and we're going to convert it into the base 10 log. So that'll generate a factor of 2.3. And then we'll factor this out of both terms, and we'll have this log minus that log. Well, when you have one log and subtract another log, you can combine those terms. So we'll do this. We'll have, this will be 2.3 q 4 pi t. And then we'll combine these two together, and I'll do that over here. So that's 2.3 q 4 pi t. And that'll be 4t t r squared s. From this, and that'll be, because we're subtracting it, we'll be dividing then by 4t t minus t1. Getting a little bit crowded here. R squared s. Okay, so the r squared s there cancels, and the 4t there cancels. Okay, so it's getting a little bit messy, but I think, and I would encourage you to just work this out on your own. What you end up with then is this stuff out front, and this is just log of t divided by t minus t1. So that's what we have here in the notes. So here it is. The drawdown during recovery is that, and here's log of t over t minus t1. Okay, so what does that mean? Well, what it means is that during recovery, if we plot the data on the semi-log axis, but instead of plotting it with respect to time like we did during pumping, if we plot it with respect to time divided by t minus t1, then it will form a straight line. and the slope is that. So here's how you do it. This is the data, the drawdown data during recovery as a function of t minus t1. So remember, that's the regular time, the time since pumping started, and t1 is just the time when the pump was shut off. And so what happens when you plot the data up is that right after you shut the pump off, t minus t1 is a small number compared to t, and so this ends up being a big number. So right when you shut the pump off, the drawdown is up here, plots up here. And then as time goes on, and that makes sense because right when you turn the pump off, the drawdown will be fairly large. And then with increasing time, the drawdown decreases, t minus t1 gets bigger, so this whole thing gets smaller. So as time increases, the data start plotting down like this. So this axis here is really plotting the data. It's kind of going in the opposite direction. We're used to having time increase in this direction, but this t over t minus t1 is increasing back in that direction. So the procedure, though, is to just calculate what this is, plot the data up, and fit the line to it, get the slope, and then the slope is going to be equal to this guy here. And so you know what Q is, and you can use it then to solve for T. So the recovery data gives you another opportunity to solve for the transmissivity.